Okay, so we're back again, and we're going through this derivation. So I kind of sketched out how we're going to take this approach. We're going to assume displacements, which are going to pull out the different columns depending upon where I put the one, either here or here or here or here, and that pulls out the 4 columns. And then we're going to use these loading situations to actually get the forces, if you will, from strength of materials type of stuff, okay? All right, so let's do the first column. And I have to go to a meeting in a second, so maybe I'm not sure how far I'll get on this. But so we're going to do the first column. These are the solutions that we pulled out, and I went over a little bit of stuff like how to get things out of beam tables, although you can derive them again from the moment diagrams like you do in mechanics materials, but this is from the beam tables, and you be a little careful about the sign conventions because that's actually very important. Okay, so let's look at the first situation. So we want to get basically the first column. So when I do that, I'm going to assume that the displacement vector is as follows: 1, 0, 0, 0 to extract that first column of the stiffness matrix. So this corresponds to the deflection at node 1 equal to 1, and then the deflection at node 2 equal to the rotation at node 1 equal to the rotation at node 2. All those other ones are 0. So if you look at what that kind of, if I try to sketch it out, here's node 1 and here's node 2. Basically, we're looking at something that, oops, I'm sorry, I did the wrong one. That's node 2, that's case 2. So if we do, so we're basically looking at a situation that looks like this. Just redraw it. Do it over here. So here's node 1. It deflects by a distance of 1. And it has a slope of 0 here and a slope of 0 here. And obviously, it does something like this in the middle. So this side is fixed. Okay? Okay. Now, if you look at this, and we multiply this by the stiffness matrix. So if we take K, and now we multiply it by 1, 0, 0, 0, that is just simply going to give us the first column, which is K11, K21, K31, and K41. So that's the first column of the stiffness matrix, all right? And that has to equal, this is KD, that has to equal the forces. So that is F1, M1, F2, M2. So this is F1, and that's M1. Then we have F2 and M2, okay? And so what you can see here is that actually F1 has to be equal to K11, M1 is equal to K21, F2 is equal to K31, and M2, this moment, is equal to K41, all right? And now we can do sum of forces in the y direction. And that's going to give us, they have to go to 0. So that gives me K11, I'm looking at this, you got the K11 force plus K31, that has to equal 0. I can also do sum of moments. And let's do sum of moments around, what point do I always do? Doesn't matter, but let's do it around A. That has to go to 0, or node 1, if you will. We'll do it around node 1. Let's do it around this point. So that gives me K21 plus K41. That's the moment 1 and moment 2. Plus the moment from the force at node 2, K31, and its moment arm is L. And that has to equal 0. So that's two equations. We need two more. So this is where we're going to use what we know from this case. All right. Now we know from this case, given P and M, and in this case P is going to be K11, and M is the moment at node 1, that's K21, we can get the slope and the deflection. All right. So here we go. So let's first use the deflection. So we know that the deflection at x equal to 0 has to equal 1, because that's what I prescribed it to, right? Right up there. Now when I do that, and I use the equation I derived before, that equation, just to recall, I'll do the substitution and then we had P L cubed on 3EI minus ML squared on 2EI, all right? But in this case, P, that's the force, that's K11, and M is going to be this moment, that's K21, and that has to equal 1. So that gives us this next equation, which is that K11 times L cubed over 3EI minus K21 times L squared over 2EI equals 1. Now doing the same thing with the the rotation at x equal to 0. Now that we know is 0, and again, it's been prescribed that way. So again, we recall what we derived in the previous video for this situation, that the rotation is this equation, and we put in P equal to K11 and M equal to K21. So this is minus PL squared 2EI plus ML on EI, and that's going to equal 0. So this gives us minus K11 L squared on 2EI plus M is now, that's K21 times L on EI equals 0. Okay? So now I have 1, 2, 3, 4 equations to solve for 4 unknowns, and they're not that hard to do. You can kind of bounce around. In the old days, when I was a younger, better professor, I used to actually, just do the algebra. But I have developed in Mathematica, basically, I just write them down in Mathematica and solve them. So here's Mathematica, right? And you can see here I've typed in those first 4 equations, and then I solve them, and it immediately gives me that here's the stiffness elements, right? Okay. So that is the solution. So basically you solve 1, 2, 3, and 4. So solving equations 1 through 4, we can get that K11 is equal to, well, let me pull the Mathematica thing up again, put it to the side. I don't need this anymore. Do it that way. K11 is 12 EI on L cubed, which is what we said it was in class. K21 is equal to 6 EI on L squared. K31 is equal to minus 12 EI on L cubed, and K41 is equal to 6 EI on L squared. All right. Let me pause. Well, should I do the next one? Yeah, we'll do the next one real quick. I think it's really time for me to go, but maybe no, why don't I stop there? The rest of them I can do relatively quickly. I should keep that up for a little bit longer. There you go. You guys can see that. Probably probably hid the last element behind there anyway. Yeah, I'm sure I did. So here are the results. It's the same as we get in the Mathematica routine. Okay? And I'll pause here, and then we can, I'll do the last 3 columns